Okay, so now I can't, okay, I don't want to anyway. Can't confine myself just to some region R that we arbitrarily define. What I want to do is I want to talk about the region D bounded by your closed curve. Okay, now if the region D includes the curve itself, then it becomes a closed region, and we can, then continuity implies uniform continuity, but again, take my word for that for the moment, because we haven't proven that. And I'm taking my word for it for the moment until I do prove it. Seems quite obvious. I haven't written out the proof, and who knows what might happen. And incidentally, this is how you prepare a lecture. You keep screwing up until you got it right, and then you go in and act like you had it right all along. Okay? So I could do that, assuming I can eventually get it right. Anyhow, that's not what we're after here. Okay, D, simple closed curve, and here's the little region R in D, and then we know we're going to divide D up into a bunch of regions, because I've already talked about that. And I'm not going to try to make a meticulous picture. But here's your R, and of course you've got a sample point somewhere here inside of R. So there's our region in its context. Okay, and then what I've said, if I can assume uniform continuity, is if these statements hold, not for the region R, but for the entire region D. And if I do that, then I can choose a delta X and a delta Y to use for my grid here, based on the behavior of the function in the whole region D. So I'm going to change the R to D. I think I've got one up here too. And now, if I choose my region R, such that delta X and delta Y are both less than D, impose a delta X by delta Y grid on D, and it should be clear what I mean by that. And now let R be any rectangle in the grid. Now I can say what I've been wanting to say, and what I've actually said all along, that you have this, okay, and in fact, you have this as well. So if you got a delta interval from here to here, and a delta interval from here to here, okay, everywhere within this delta interval of X star, Y star, My varies by less than epsilon over 2, and Mx varies by less than Mx over M, whatever I was saying, okay? My varies by less than epsilon over 2, Mx varies by less than epsilon over 2. And from that you can conclude that everywhere within this delta interval around this point, which will include your rectangle, as long as delta x and delta y are both less than delta delta, no matter where x star, y star is in the region. Okay, if you put it in this extreme corner, well, delta x is still less than this delta, so this region here is still going to contain the region R. Okay, now from the fact that say all the words right, that my varies by less than epsilon over 2 from its value at x star, y star, and that so does nx, you can conclude that the difference in magnitude between the value of m on this edge of the rectangle and on this edge of the rectangle has to be less than epsilon over 2. Okay? And similarly with your nx. And I might not even have to use the epsilon over 2 because I was thinking in terms of the net difference between values here and here, which would be a Pythagorean theorem type thing, and I don't think I need that. Okay, so let's just say what we've hopefully established here, that you can choose a delta x and delta y grid such that on the entire domain bounded by your smooth, or by your simple closed curve, doesn't have to be smooth, and such that every rectangle or every region within that grid, doesn't even have to be rectangle, could be one on the boundary where you have 3 straight lines and then a little bit of a curve, that on every such region, my and nx vary from their values at your sample point by less than epsilon over 2. Once we've got that established, the rest is easy, relatively easy. We still have the question of uniform continuity, because you need uniform continuity to say that there is just one delta for the given epsilon that applies over the entire region. Okay? Okay, well, we'll try to clean this up a little bit more and go on.